Okay. Is this working? Yep, there we go. There we go. Technology. Okay, so the thing that finally got me to turn on the live office hours was because we learned a really cool trick. And people were like, whoa, how does that work? So we're going to do a really cool trick. And it was about how we calculate buffer capacity. Right? So when we look at buffer capacity, we're looking at our buffer. I'm exaggerating the buffer area so we can see it more easily. We're going for, if we were doing acetic acid, we're going from 4.74 all the way down to 3.74 and all the way up to 5.74. And essentially, to find the buffer capacity, we want to find the volume to the start. That is the volume of titrant to the start. And we want to find the volume of titrant to the end. And the thing that I said very flippantly, very quickly, was like, oh, calculate the first one, multiply that volume by 10, and that's the end. Just multiply by 10. And the thing I wanted to show everybody was, why is that true? So if we think about calculating the volume at the start, we'll do that in green. So if we're doing the volume to the start, we are going to do pH equals pKa plus log A minus over HA, concentrations. I know my pH is 3.74. I know my pKa is 4.74. That's log A minus over HA. 3.74 minus 4.74?
1.
Negative 1. 10 to the power of negative 1? Oh, you can do that. 0.1. 1/10. 0.1. 0.1 equals A minus over HA. Yeah, do that in our head. So that is at the beginning. Let's also, real quick, let's look at the volume to the end. Now here, essentially, we're going to be using Henderson-Hasselbalch again, except for we're going to have 5.74 minus 4.74 plus, equals log A minus over HA. 5.74 minus 4.74? Now it's 1. 1 to the 10 to the power of 1? 10. So it turns out you end up with these really nice factors that allow us to do the calculation. And from there, you can just keep going. But the fact that you have these whole numbers that kind of give you these ratios, that's what makes it work so well. Now, we can plug in the stoichiometry in addition to everything else just to prove that this works. We're going to have 0.1 equals molarity of strong base times volume of strong base divided by molarity of weak acid, volume of weak acid minus molarity of strong base, volume of strong base. So we need to pick some numbers so we can actually do this calculation. Favorite number? 3. So we will do 333 milliliters of somebody else's favorite number. 6. 0.6 molar acetic acid. And then I need, see, one more favorite number.
17.
Wait, 17?
Short.
Oh,
We can do 0.17?
yeah, it's just going to make the numbers really weird, but let's do it. Let's do it. With 0.17 molar, something close to 0.6, but let's just go with this. Let's see. With 0.17 molar strong base. And the question is, I didn't write the question. What is buffer capacity of? What is the buffer capacity of 333 milliliters of 0.6 molar acetic acid titrated with 0.17 molar strong base? Now, the reason this is going to throw the numbers off is because you notice 0.17 is about a third of 0.6. So that means that I'm going to need 3 times as much. I'm going to need about 1,000 milliliters of titrant to make this, to get to the equivalence point. That means I'm going to need about 500 milliliters to get to the midpoint, probably about 50 to get to the beginning of the buffer region. But let's go ahead and plug these numbers in and see what happens. And essentially, if you look at this bottom equation in green, which you can see on the screen, you can tell that we know everything except for the volume of strong base, right? We know the molarity of strong base, we know the molarity of weak acid, we know the volume of weak acid. So we can replace all of those things with numbers that we know. And I'm even going to replace the volume of strong base with just an X because that looks easier on the eyes. So I'm going to have 0.17X divided by 333 times 0.6 minus 0.17X. And now we have to do the hardest thing in the class, algebra. All the concept work, all of that is what we focus on in the class. I never slow down and check how everyone's doing with algebra. And this is kind of the hardest algebra that we do. But it's still just algebra. You have to multiply everything over, add the 0.17x over, then divide by the total to get x alone. So go ahead and do that real quick. Do your algebra. Let's figure out what x is equal to.
And this is giving us the volume to start the buffer?
This is the volume to the start of the buffer capacity, to the start of the buffer range. I'll grab my calculator and get it too, just for fun. If you're watching at home, grab your calculator. Don't just skip ahead. You skipped ahead already, didn't you? Yeah. 333 times 1. Did I do that right? What'd you get?
106.1. Okay. So that molar absorptivity value would be 5.
Yeah.
What are we solving for exactly?
X. What is X though?
Are we still like proving why that's 10?
Yeah. So we're going through the long process of, proving it to ourselves by calculating the start, calculating the end, and seeing that it's actually off by a factor of 10. And the place where this factor of 10 is coming from is essentially, I know it looks like a factor of 100, but because of the way the math works out, it ends up being a factor of 10 for the volume. I apparently hit enter a couple times. So I got 106.8. Right? Yes.
Yeah.
Cool. Okay. Now, we are expecting over here for the end of the buffer region to just get 1,068. But let's show that that's true by actually going through and doing this calculation. We're going to plug in all of our things just like we did here. So we're going to have 10 is equal to 0.17x divided by 333 times 0.6 minus 0.17x. Notice everything looks the same.
Wait, where's the 10 coming from?
So the 10 comes from 5.74 minus 4.74 is 1. And then to get rid of the log, we do 10 to the power of 1. So let's solve. Sure enough. Right? And it works out like that every time for any buffer system we do. And you can kind of make sense when you look at this, why it works out that way. Really what happens, if you did this for all just variables, you get, let's see if I can remember. You get 1/11 and 9/11 or something like that, or 10/11. So you get 1/11 for the start of the buffer capacity, and you get 10/11 for the end of the buffer capacity. That's 10/11 of the equivalence volume. If we wanted to come up with a generic equation, we could do all of that. But why fill our heads with extra things when we can just calculate 1 point and then multiply by 10? So that's how it works. So now technically, to solve for the buffer capacity, we really only need to solve for 1 point, either at the start of the buffer range or the end of the buffer range, and we can see how they relate to each other. I didn't do this in class because if I do it in class, people don't go through the trouble of actually understanding, right? So they just memorize, great, I'll multiply by 10, which is, fine. But understanding why that works, understanding the math behind it is also important. One other question. So what we've been working on, we're about halfway through office hours. I know I started my video late, but that's okay. No one's watching anyway. We've been working on some of the buffer lab questions, the post lab questions. Most of those people who got those answers already left. So if we need to go over something again, I'm totally fine doing that.
I'm working, actually, I don't really understand a lot of part 3 for the lab, but also for this part about the DI water, I did that yesterday before I got here, but
we can do that again real quick.
Like to kind of
Let's do the DI water part of the buffers lab real quick because that one's really straightforward.
Is that the last question on the first page?
Yeah.
Last question on the first page of the buffer lab. So essentially what we've got is 50 milliliters of water with 1 milliliter of 0.1 molar base. I don't care if it's sodium hydroxide or potassium hydroxide as long as it's monobasic. Right? And you just did 1 milliliter. We could do it for 5 milliliters. We could do it for 50 milliliters. All the calculations are going to be the same. Is there any acid for the base to react with? No-ish, right? Technically, we say, actually, water acts like an acid. So we could see this reaction of the base, but that's getting into the equilibrium of water, which we usually neglect. So let's look at it in terms of the equilibrium of water, even though we're going to see that's pointless. So if we look at this, we're going to have H2O liquid plus H2O liquid goes to H3O plus OH minus. Aqueous. This is why you can't let me be lazy with the units because with states of matter, because states of matter are very important here. I'm going to set up an ice table. I'm not going to care about the liquid at all. And essentially, the base that we're adding is just going to act like a common ion effect and put some amount of hydroxide here. It's approximately 0.1 molar. If I really wanted to be more careful, I would do 0.1 molar, right? I want the concentration when these are added. Oh, no, it's not 0.1 molar at all. It's 0.1 times 1 divided by 51, right? 0.1 times 1 gives me my moles, then divide by the total volume in order to get the molarity. Let's not forget that, right? So essentially, this calculation here, 0.1 times 1 divided by 51, that's just doing an M1V1 dilution calculation that I can't do in my head. It's like 0.002. Help.
Yeah.
.0019. So
0.0019. Because 1/5 would be like 0.02, 1/50th would be like 0.002, but we've got 51. So then I'm going to start with, I'm going to say I've got 0 H3O plus. That 0 is essentially saying water is negligible, but we're actually doing water's equilibrium. So let's see how much water actually contributes. It's going to have some plus X. It's going to have some plus X. We're going to get approximately X, and we're going to have 0.0019 plus X. Instead of doing it where we solve the quadratic, right? We could solve the quadratic. Let's use the extra-small approximation. And this is why we don't need to do this equilibrium. Notice my concentration of hydroxide at equilibrium is just the dilute concentration of hydroxide. So all I had to do was find the dilute concentration of hydroxide. I don't need to do an ice table. And then I can just say my POH is equal to the negative log of 0.0019. I don't need to do the ice table. I can just take the dilute concentration of strong base. And it turns out this is the calculation. You know, we've got our titration curves. Everything we do out here is this. We're just doing dilute concentration of strong base. That's why it flattens out and very, very slowly goes up, is because as you add more and more base, you're barely adding more base to the total volume. So your concentration is changing very slowly, so your pH is changing very slowly. But it's just because you have extra base. So that's how we do the water case. And very clearly, all that matters is how much base you put in. Right? There's no reaction that happens beforehand, which is why even 1 milliliter of base totally throws the pH super high. When we were doing this with our buffer, whether we were doing our original buffer or our dilute buffer, 1 milliliter didn't change it much because that 1 milliliter of base was reacting with the weak acid, and that wasn't changing the pH very much. So that was the deionized water. What else do we want to look at? Yeah.
I had a question on 8B on the very
Yes. Let's look at problem 8. So everyone go ahead and flip to that last page. And let's look at problem 8 on the buffers lab. Okay, so when we're looking at problem 8, we essentially are doing what this lab used to be. This lab used to be right off the bat, we give you just these things. Hey, come on in. We used to say 250 milliliters of 0.1 molar buffer. No, so 0.1 molar with IND over HIND equal to 0.2 for thymol. We give you this.
Question?
Yeah.
To start. I'm having trouble remembering. So the IND is the yellow, right? Or is that the HIND that's the yellow?
I can never remember. If we check in the,
which one's more acidic?
If we check in the background, yeah, the HIND. I'm pretty sure the HIND is yellow and the IND minus is blue.
Okay.
It also depends on which indicator we're looking at. I think for all three in this lab, the acidic version is yellow and the basic version is blue. And if you look in your background information, that's there. If we're using different indicators, we could have it flipped. We can have different colors, clear to pink if we're doing phenolphthalein, yellow to red if we're doing, what is it, like thymol red. You can do like one of my favorite indicators, cabbage juice. Purple cabbage juice, you can get like 6 or 7 different colors from purple cabbage juice by just changing to the right pH. So this is what the lab used to be. We would give you these 4 pieces of information and say, calculate. First thing you do with buffers, get these 4 things, good luck. And the reason that this is a little bit complicated is because there are essentially 2 systems we're looking at. We've got the indicator system, where we're going to use the Henderson-Hasselbalch equation pH equals pK. I'm going to call it pK IND, so it's specific to the indicator, plus log IND minus over H IND, our weak under our conjugate. Right? Everyone's good in. There's like 2 other chairs in here.
I was just waiting for her.
Oh, okay. Then what we're doing is our indicator system is what we're trying to control using our buffer system. In this problem, we're going to use a buffer system of NH4 plus NH3. And this will also use the Henderson-Hasselbalch, but we'll use pH equals pKa plus log of NH3 over NH4 plus. And the reason that this more complicated version of the lab is probably better in terms of giving some idea of the usefulness of buffers is this really gives you an idea of why buffers are interesting, right? So essentially, we're creating a buffer to control the expression of this other system. We're in this indicator, we're either expressing yellow or we're expressing blue. But we do the same thing with amino acids. We do the same thing with other physiological processes. Our entire body is essentially like different buffered systems in different areas. And the buffer is a particularly regulated pH to control the expression of another system. So then we can add acid or we can add base to change how that system is being expressed. The buffer regulates the pH to give us some response of a more interesting system. You can imagine if we did this lab without the indicator, you'd just be looking at clear solutions all day. It's not that interesting. It only becomes interesting when we're using the buffer to regulate something else. Question?
What is it, pKIND?
I'm using that to specify rather than doing a pKa, so it's specifically to the indicator or a system of interest.
I guess I just
versus,
thought, like, since HIND was the acid.
Oh, I could do pKHIND. This is just the, yeah, let's do that. Okay. It's just to make sure, the main thing I wanted to do is make sure that it's different than pKa, right? So if I wanted to be more careful, I could call this the pKa for the indicator. Is that better?
Yes.
Okay. So this is the pKa for the indicator system. Now, I don't want to do the background problem or the problem for you, so I'm going to change some of these numbers. And we're going to do it from these other numbers. I'm going to pick simple 100 milliliters. We'll do 0.4 molarity. What's a good ratio besides 0.2? Favorite number?
I already did my favorite.
Oh, we already did your favorite number.
8.
We'll do 0.8, right? So we can look at this and we can start to kind of plug things in and figure out what's going on. We can figure out what our target pH is, right? So we want to control this system of interest, and we want to control it so that there's this particular ratio of how we're expressing the system of interest. So we're going to have log of 0.8 there. You have to look up the indicators pKa given in the background. 8.9. So we're going to have pH equals pKa, or the pKIND plus log of 0.8. And calculate. I can't do that in my head. Ooh. Minus minus 0.7? No, minus 0.1. So we're going to get like 8.8?
Yeah.
Yeah.
No way. Wow, I can't believe I did that right.
That's impressive.
So, not surprisingly, notice our ratio is pretty close to 1, so we expect to be close to the pKIND, and we are. The 0.8 means we've got a little bit more acid, a little bit more of the HIND, a little bit less of the IND minus. So we expect something to be a little bit more on the acidic side, 8.8. This target pH is now what we're going to use to define our buffer system. Question?
How, like, I know you're not doing like our specific problem, but like, how would we find how much of like the IND or HIND that was at? So just like an X table?
No, so most of the problems we're doing are not actually asking us to solve for IND or HIND. They're asking us to find the ratio. There are places in the lab where you do find the IND or the HIND, but you're using Beer's law to do it. And the molar absorptivities that are given in the background in order to do that. Okay. So after we have our target pH and we plug that in down here, after we plug in our target pH, we're essentially doing the prep activity again. Right? We're doing follow along with the background prep activity. Saying, ooh, there is a piece of missing information in problem 8. Do it for a 0.1 molar total concentration, just like we did for lab. But that is definitely missing from problem 8.
Wait, what?
So at some point, you need to know the total concentration of your buffer. And I'm saying just use 0.1 molar, the same thing we did for the lab. If somebody already turns it in and they do it for a different concentration, as long as you did it right, you'll still get credit. It'll just be a headache for me. If everyone does 0.1, it'll be less of a headache. Then I'll be happier when I'm grading, and I'll probably give everyone better grades.
Here we go.
Always make your teachers happy when they're going to grade. So, not for your individual grade, but overall, if they're in a good mood when they're grading. This is not a call for bribe. I have to delete this video now. Good grief. So let's go ahead and let's finish this calculation. We've got 8.8, and this is where most people make their biggest mistake. They just plug in 8.9 again. But remember, that was for the indicator system. We now want to do it for the buffer system. What's the pKa of NH4 plus? We have to look it up. If you didn't look it up, I know the Ka just because we did this problem not that long ago. It's like 5.5 times 10 to the minus 10, which gives you a pKa 9.26. That sounds right. Right, so we've got 8.8 equals 9.26. Notice, because we've changed systems, it's not going to be exactly the same, which is what we expect. This still works because our target pH is still within plus or minus 1 of our buffer system. Questions?
So why would you look up the Ka for NH4 instead of NH? Like how do
So you would look up the Kb, honestly, you would look up the Kb for NH3, then convert it to a Ka so you can use the original Henderson-Hasselbalch rather than the basic Henderson-Hasselbalch. Remember, what we found out in class yesterday is we never need to use the basic Henderson-Hasselbalch.
Okay.
Because whenever we're in the buffer region, we get to pick whether we're looking at the expression of acidic behavior or the expression of basic behavior.
So if you took the Kb of NH3, converted it to Ka, it would be the same as that?
That should be the same.
Okay.
Yeah. Unless I completely misremembered what the Ka for NH4 is.
Okay.
So at this point, we can solve for NH3 and NH4. We also know that the concentration of NH3 plus the concentration of NH4 plus is equal to 0.1 total concentration. This is going to allow us to find the concentration of the individual things. Then we can multiply by the total volume to get the moles. Then we can take the moles and we can figure out how much acid and base we need. Just like the prep activity. Again, this is a little bit more complicated than the prep activity because we are dealing with two systems. The indicator just defines our target pH, and then we're doing everything the same. Just imagine if you had to do that first. That's just such a bigger headache. But again, it is more useful in terms of expressing the usefulness of a buffer. Question?
I had a question on number 6. Those solve questions.
Are we ready to? Let's give everyone a minute to think about this and see if they've got any questions. Then we'll move on to number 6.
Are you supposed to go backwards?
You know, it's like, yes. Apparently the video flips on my screen, but for everyone else it's the right way. I don't know why YouTube does that. Interesting. It has something to do with like production. I don't know. So yeah, let's go ahead. Let's finish solving this because we should all do it for the actual numbers for your lab rather than for my numbers, and then we can check your work with each other. I'll do the rest of this problem.
Wait,
Yeah.
sorry, question.
Mhm.
So I just did it for my numbers. So basically for the problem, it's
Yeah,
at
0.2 there.
0.2, yeah.
Mhm.
And so the pH comes out to 8.2. And so that means you would have 8.2 and then 9.26. So
So
that's like very borderline.
this is
Right?
very borderline, probably, so that it's good that you're being cautious when you're at the edge like that. Probably still okay. Probably still okay, but good to be cautious, right? You start to get to when you get to those edges, when you get to the edge of the buffer range, edge of the buffer range, you start to get into the risk of excess small approximation failing.
Can I write that all out just to make sure?
Yeah, I'm going to finish this problem. So it's not going to be the same as your numbers, but let's go ahead and do this. So,
Sorry.
Yeah.
For the NH3 plus NH4 equals 0.1, is that because the total molarity is 0.1?
total molarity is 0.1. So I'm going to go ahead and solve this. I've got a calculator somewhere around here. Answer 346. So then I can go ahead and say 6 plus 1. That goes to NH4 plus equals.
Then you know how many moles of OH you have. Okay? And then you figure out how much you lost.
0, 7, 4, 3. Means my NH3 concentration is.
Okay. So once you calculate your moles, then you have been added with the active
7.
so you create more. You get
So, I did something wrong.
Oh, no, we didn't.
What's that?
We didn't.
But these two numbers. Oh,
Yes, you did.
because for my system I wanted 0.4. Those add up to 0.1, but they're not giving me the. Oh,
Because you
Right.
just should have
Okay.
put 0.4
no,
instead.
this is totally fine. I divided these two thinking I should get 0.8, but I'm in a different system, right? This is the NH4, NH3. I divided them thinking I should get 0.8, but you shouldn't get 0.8. I made a mistake in my head. Don't worry about it. I don't know, right? You should get whatever you got from, I should get 0.346. And that's what I got. I'm fine. I just made a mistake in my head. Don't worry.
How did you, once you found the NH4, how did you find the NH3?
I did 0.1 minus NH4 equals NH3, right? So then I can go ahead and, for my problem, so I messed up the problem I meant to do, made it more like yours. I did it for 0.1 molar instead of 0.4 molar. I can tell I did things right because these numbers add up to 0.1. And if I take the ratio, I get 0.346. That's all good stuff. I can then take my total volume for all of you is 250. For me is 100. And I can get my moles. Moles at the excess point of NH4 plus would be 74.3. Nope. Too many zeros. 7.43 millimoles. And the moles at excess for NH3 would be 2.57 millimoles. When I add these up, I get my total amount, 10 millimoles, which I could have figured out just by doing 100 times 0.1. That's going to be my acid at start, adding those two numbers together, or just jumping and doing 100 times 0.1. Either way. Yeah.
This is like a more general question for the midterms. I'm about to leave. Do you think, so would it be good to study like lab calculations for the midterm? Like, do you think there's going to be, since we haven't had that many quizzes and things, will there be calculations like there was in the lab on the midterm? Okay.
Yeah. The lab calculations, homework 4, homework 5, a little of homework 3. There was some acid-based stuff on homework 3. Okay. So a little of homework 3, homework 4, homework 5 in labs.
Okay.
That's pretty much all we've done since the first midterm.
Mm-hmm.
The last thing we need to do to finish this problem up is we need to use one of those 5 simplifying ideas. The amount of NH3 we have at excess is also that's also the moles of strong base we want to add at the start. So we can use the moles of strong base at the start and the moles of acid at the start to essentially do our stoichiometry. We're going to take the moles of acid at the start, multiply by the molecular weight. That will give us the grams of ammonium chloride we want to start with. We take our 2.57 millimoles of strong base. What concentration of strong base? 1 molar, so that's going to be the number of milliliters, 2.57 milliliters. For my problem, you should get something different for your problem. Any questions? So again, this is just like the prep activity that most of you did correctly, and it is just like the walkthrough in the background. The things that are really confusing in the background are these last 2 things I did, right? The fact that these 2 moles add up to give us the moles at the start, that comes from the stoichiometry. And the fact that the moles of strong base at the start is equal to the moles of conjugate base at the excess, that's also due to the stoichiometry. I'll go ahead and make that stoichiometry table real quick to show it, just to make sure there's no confusion. So the stoichiometry that's happening to make this buffer is essentially an H4 plus. There's a Cl there for getting our correct molecular weight. plus OH minus goes to NH3 plus H2O. I'm going to do a start, reaction, excess. The things that I calculate are my excess numbers. That is to say, I know that I want 7.43 there. I know I want 0 there. And I know that I want 2.57 here. I know that I start with 0. That means this 2.57 must come from plus 2.57. Because 0 plus 2.57 is how you get 2.57. Now, this defines my limiting as 2.57 and negative 2.57. This means that I must also start with 2.57 here. So that way it goes to 0. This line is what tells me my moles of NH3 at the excess point are the moles of hydroxide that I start with, because I want to make sure that my moles of hydroxide are the limiting reactant. And that's why I've got minus 2.57, minus 2.57, plus 2.57. It's because my hydroxide is the limiting reactant. You'll also notice there's a 1-to-1 ratio through all of those that we're not worrying about. Now, the last thing that I need to get, so that's how we get that one. The last thing I need to get is the number here. And you can essentially say some number minus 2.57 equals 7.43. So I'm just going to add the 2.57 and you get 10. And so I know that if I had 10 minus 2.57, I get 7.43.
Okay.
So that's where I get these two numbers added together, gives me my start value, and this number is my start value. Don't say it too loud. I don't want it on video. Yeah, you don't get the answers. You have to do the calculations yourselves.
Was there a question?
No, she said thank you.
Yeah. Question.
So, yeah, for 7.43 and 2.57.
Uh-huh. And those were for my values.
Well, I know those are
Okay, cool.
values, but how did you get those? Because I know
Oh,
you
so
multiplied by.
I took my concentrations times my total volume.
Oh.
And my total volume was 100 milliliters. So you're going to do your
Okay,
concentrations
gotcha.
times 250, or if
Sure. Okay.
if you made a double batch, I don't know who would, but then you multiply by 500. Whew, so that should be, oh, we still have to do number 6, huh?
Yeah, someone had a question on said.
Yes, please. What's question 6?
When you added both indicators to your buffer samples, did you
Oh.
see both forms of the indicator in both samples? If you did not see both forms, why or why not?
Do you see both?
I have a quick question, really quick.
Oh, shoot,
You don't
yes.
have to raise it. So do we convert it to grams since it's solid? for
Yes,
the
you convert to grams because it's solid.
Okay.
I left it in millimoles. You want to multiply by the molecular weight to get it to grams.
And that will be found from the periodic table, or is it dependent on?
Periodic table. Okay. Question 6. To do question 6 properly, we need to know both the indicator systems that we're looking at. So we've got bromothymol blue. And bromocresol green. I almost spelled green with an L. I don't know why I did that. I spelled bromocresol right and then almost messed up green. Chemistry problems, right? Okay, so what is the indicator's equilibrium constant for bromothymol blue? You can just pick up the phone and hang up on me. Thanks. Just during office hours, if it's not office hours, I answer. It's almost always robocalls.
I get so many of those. It's ridiculous.
Okay, terrible side story. It was not me, but I had
It was definitely you.
no, it wasn't me. But another instructor here had a student who was like, "Hey, you never responded to all of my messages." And the instructor says, "What are you talking about?" He's like, "I was texting you for the last week about like making up this stuff." And they're like, "How were you texting me?" They're like, "You never was online." It's the office phone, texting the phone number for the office phone, and apparently not getting errors that it wasn't working.
That's nice.
So they're like, "No,
Question is who tries to text us?
landline."
Yeah.
Okay, I will answer this. Hello, this is Jen.
A bunch of my professors give us like their personal phone numbers, like text.
Oh, she
Yeah, my senior
right
project.
across the hall. This is
Senior
my
project
first
professor.
number.
And she never answers her emails.
Oh,
So I
man,
know
no,
somebody like
no,
in
she
another
changed
class.
offices.
Yeah.
I'm afraid
She's
I
like,
don't know
"I'll send her email." I'm like, "Here you go. Here's her text."
Phone number. I know, I had one of like my professors.
Oh, drat, okay.
It's 'cause I'm, like,
Do you have her email address? Because that would be the quick way to get a hold of her.
It's like talk about my paper, and I was like, NH3, this is like
Um,
unbelievable. It was like, and it was like 8:30 at night too. So yeah, too.
Okay,
That'd be
So,
too early.
right,
Too
yes.
I don't know like anything that's going on, like with any of
Yes.
this. Does he explain
Pardon?
anything some of his past office hours?
Yeah.
It's like,
No, I teach chemistry. And she was working last spring, she was working here in the chemistry department. So, you might.
oh no, that was what I was gonna. I wanted to figure out really. Yeah, I have no idea. Like,
I'm afraid I don't know who we're in the middle of office hours.
do you know if this is like on his past office hours, like yesterday or
Now it's
anything?
back.
Like
No,
any
it's
of
not.
the.
Okay,
What is this?
so bromothiamyl blue. Do we know the indicator constant for that? Background information? Should be the other one. Let's have a look here. There it is. Bromothiamyl blue is 7.1. And bromocressyl green is,
So it's the PKA.
yeah.
4.7.
So we can use this information alone to figure out what's going to happen, right? So we can look at bromothiamyl blue, and we can say down at 6.1, it will be yellow. And if we go all the way up to 8.1, it will be blue. All through between there, it will be green. I don't have a yellow pen, so I use red. We can do the same thing here. If we're down at 3.7, we're going to be yellow. If we go all the way up to 5.7, it'll turn blue. Then all through the middle, it'll be green. And I'm sorry, I don't have like a good gradient, but keep in mind, this will go from like a yellowish green, it'll change the shade of green throughout the process, right? Starting out with this kind of like yellowish green all the way down to like a bluish green. In the direct middle, you'll have your like real green. So when we look at this, we can say, okay, where did you make your buffer? What pH did you make your buffer?
I have to look at my notes.
Mine was 4.7.
So if you made your buffer to be 4.7, you'd be right here in terms of this one, and you'd be like all the way down here in terms of this other one, right? So for one of them, you've got some ratio of the yellow and blue species. But for this one, you're going to be all the way down in just yellow. What was your pH?
7.1.
So if your pH is 7.1,
Okay.
you're going to be right here in the middle for this one, and you're going to be all the way up here for the second one. So we can just think about it in these simple terms, right? The other way to think about it, if we want to be a little bit more complicated, is to say you are outside the buffer, or you're outside of the midpoint area of, or the midpoint of your buffer is far away from the midpoint of your indicator. And so you're only going to end up with one species.
So my pH was 7.28. So when asked like which indicator was better, would it be the blue because you're like in the green area, or would it be the green because you're like well past and like it's
Remember,
it's blue?
there's a key phrase that we have for when we're thinking about indicators. When we want the indicator's midpoint to be close to our target pH, right? So we want the indicator's midpoint to be close to our target pH. If your target pH was 7.2, the bromocresol green is going to be terrible, and the bromothiamyl blue will be good.
Got it. Okay.
So when it says, did you see both forms of the indicators in both samples? What was that?
So did you see the HIND and IND of both of them?
Oh.
And it's kind of tricky, right? Because technically, probably you could say yes, based on the spectroscopic data. But remember, when you get to a peak height of like 0.01 for your absorbance, you're kind of in the noise, right? So you're just kind of picking up nonsense if your value was close to 0.01.
Should I just do it like based off what we saw visually?
Yeah, I saw visually, and I would just discount any values above like 0.05. I would say that was really there for your absorbances. And you should find that for one of these, you had an absorbance that was like 0.02 or 0.01, and the other was like 0.4. And for the other one, you had like 0.3, 0.2. So it's the one that you had 0.3, 0.2. That's the one that's useful. Is that all the questions for the lab? I figured that's... I'm kidding. I think there's a couple more.
Can I just ask about number 3?
What's number 3?
Just to make sure I got this right. So when you dilute the buffer, does the pH change? Should it, and explain your observations. So it did.
It
and
did.
It became more basic.
Oh,
Yeah, that's why I was confused.
more basic.
That's why I was confused.
Okay.
Yeah,
How much more basic did it become?
It went from 7.14 to 7.65.
Oh, mine.
How much did yours change?
Mine went from 7.10 to 7.11. Like,
Oh, that's fine. Wait,
It
what?
didn't go down.
What water did you use? Yeah, were you one of the groups that I had used deionized or tap water instead of deionized water? Okay.
It's supposed to be more acidic.
Is it supposed to?
Yes, we went over
Well,
that.
so let's think about theoretically. Well, let's think about this in
At
terms of the
least I-
different
okay.
parts.
At least I know like that wasn't right because I was like trying to justify
Good,
it. And
yeah.
I was like, this does not make
Should I
sense.
just say like it went up, but it should have gone down?
Well, should it have gone down even? Theoretically, if we look at this, if you've got some buffer, right? You've got your Henderson-Hasselbalch is pH equals pKa plus log A minus over HA. Let's say you had a concentration of 0.4 and a concentration of 0.6 for your A minus over HA. And then you dilute by a factor of 10 so that you go to 0.04 divided by 0.06. Are you going to get a different pH? Is your fraction going to be the same? Right, since you're changing the total volume, since you're doing the dilution the same for both parts, because you can't do it for one part or the other, technically your pH should not change, right? If we were doing this with good water, water that had the correct pH, you would see no change. What some of my students did was they measured the pH of deionized water, and they found that their deionized water was slightly acidic. That slight acidity can mess with the pH. More importantly, and the thing, if yours went more basic,
You're gonna love this next one.
so if yours went more basic, the likely culprit, dirty glassware.
Because that was with 1 milliliter.
Uh-huh.
The total of 5, it went from
Hold on. So that was your dilute with 1 milliliter?
Yeah.
Oh, then your pH should definitely go up. What was your dilute before you put anything in?
7.14.
Did it go down? So here, there's three things going on in this part, right? So there's the idea that just adding water shouldn't affect the pH. Yeah. What question 6 is asking is, did just adding water affect the pH? Not when you add base. When you add base, the pH should definitely go up, and it should go up by a lot. But just when you added water, what happened? And again, we're revamping the lab a little bit, so I think there's not a spot to record that data. So you might not have recorded that.
So this was, I guess I'm just confused on which part we're on. So we're on, this is part 2.
Right, part 2.
Yeah, I'm looking at like my notes here.
We're looking at
So you put
the
the buffer solution in and then 180 milliliters.
then your recorded pH of your
went to
dilute buffer.
7.18.
That
So that's
slight
1.04.
change, yeah, that slight change is fine,
Okay.
right? And most people saw their pH go down because of dirty glassware and possibly a little bit the acidity of deionized water.
So it should have gone up.
Should have stayed.
Just adding water should have stayed the same.
Okay.
Now, when you add 1 milliliter of base on top of that, if you're adding base, pH should increase, and it should definitely increase there.
Okay, so then that should have been.
Yeah, looks like you've got the right idea.
What increase DI water is acidic?
That's a fantastic question. So why is DI water acidic?
Being in contact with carbon dioxide
Yeah.
in the air.
So it turns out there's a chemical reaction that we should all be really familiar with from 127 that a lot of us have forgotten about. And that is HCl plus Na2CO3 goes to, and actually you should be familiar with it from 128 as well. When I add these two things together, I make carbonic acid. Carbonic acid has a decomposition equilibrium to H2O and CO2. And this decomposition equilibrium is CO2 favored, especially if you're not trapping the CO2 at all. Now, the fact of the matter is this is still an equilibrium. So if there's CO2 on top of a container of water, that CO2 can dissolve in to the water and react with the water to form carbonic acid, which makes your pH become acidic. Now, this happens more in deionized water instead of tap water. And I had some students do this lab with tap water, and the results actually came out better. That's because essentially when you think about tap water, you've got all of the ions, you've got other things in the water already, which make it harder for the CO2 to dissolve in, right? The water's already interacting with other things. So once you have deionized water, the water is just there able to interact with O2, CO2, N2, all of the things that are in the air above it. We actually, it was a year or two ago, I actually got the stockroom to do degassed water, which is to say they took a carboy of deionized water and they put it under vacuum to pull all of the dissolved air out of it. And that deionized water, perfectly 7. Perfectly 7 for about an hour and a half. And then the gas started to dissolve back in and the pH started to drop again.
Wow, that's cool.
Yeah, so it worked. So I had 2 lab periods in a row, and we got the degassed water, and the first lab period used the degassed water, and we were like, wow, it worked. And then the second lab period came in, and it didn't. It was like the one that didn't work again. I was like, and it had already absorbed CO2 again. So, and I'm not willing to make the stockroom degas the water like every few hours. So,
There you go.
tap water works great, but not for this week's lab. This week's lab, we have all kinds of contamination issues, so no tap water. Back to deionized water.
Speaking of this week's lab, can I ask you a question about this week's lab?
Let's make sure. Any other questions about the buffers lab?
I have one more question.
Yeah, and then we got one over there.
It says the concentrations of indicator species in the original buffer for the absorbance and posted molar absorptivity. What did we do there? We're supposed to do like resolve there.
Yeah. So in that situation, you should have measured absorptions.
Yeah.
and in the background you have molar absorptivities.
Oh, okay.
You can use that information to turn the absorptions of IND and HIND into concentration of IND and concentration of HIND. Plug that into the Henderson-Hasselbalch to get a pH.
Yeah, I get it.
Cool. And then question?
Yeah, I was just looking at number 4 on the background questions. It says, explain the difference you see in the size of the change of the pH for the 3 different solutions, original buffer, dilute buffer, and which is added.
Yeah.
So there was obviously, for me anyway, there was like the greatest difference in just the plain water and then diluted buffer and then original buffer.
Yep.
But I don't really understand what it's asking.
So that's exactly what it's asking about. Where did you see the change jump? So for the deionized water, 1 milliliter, it changes.
Yeah.
For your dilute buffer, 1 milliliter doesn't really change it, but 5 does. For the original buffer, 1 and 5 both don't really change it.
Okay.
And so the idea that you're supposed to think about there, and I'm not going to give you the answer, but I'm going to do what you think about, is how does each of those solutions have a different buffer capacity? What's the buffer capacity of the original versus the dilute versus water? I'll tell you, water has no buffer capacity. Right? It's not really a buffer. So how does the buffer capacity change as you change volumes, as you change concentrations, things like that? Are we ready to move? Oh, yeah.
So I know you explained this in like the previous office hours,
Mhm.
but for like the first page, when you're doing the Henderson-Hasselbalch equation, you're using your pKa. Do you use the pKa that you got in your pre-lab? Like when you're trying to calculate?
Yes,
pH?
if it's just your buffer, yes.
Okay.
The only place where you have to worry about a second pKa is part 3, where you're dealing with the indicator as well.
Okay.
Okay. Should we look at this week's lab?
Yes.
What are the questions for this week's lab? So this week, and I forgot to make the announcement in class, but hopefully you all know this week is the sulfur lab. No,
Oh my god, you almost just gave me a heart attack.
sorry, fluorine lab. Fluorine lab this week.
I literally almost just died in this chair.
I'm so sorry.
I'll have you know.
So sorry. I'm thinking ahead.
How long does it take you to do the
I mean, it always takes me a long time.
So this week is the fluorine lab. And this week we have to be really careful. Fluorine, chlorine, bromine, iodine, all common contaminants in tap water, right? Chlorine especially, right? Sodium chloride's everywhere. So we have to be really careful this week about contamination. Sorry about freaking you out. What are your questions?
I almost had a heart attack.
Sorry, before I go, if you could consider doing extra office hours on Thursday again, like you did last time,
Yeah.
that would be clutch. That would be
Okay.
awesome. Just putting it out there. And
Think about it.
thank you very much.
No worries. See ya. I've got to figure out how busy I am this week. I should be
Or
able
we could
to.
FaceTime you.
It'd be pretty nice.
That's what I'm doing. It's just there's only one person watching now, because you're all here. It's 3-dimensional FaceTime. Sorry. What's your question?
Okay, so for part B of the chloride test, I just don't even really get what's happening. Like it says in like the green, the first edition of, what is this, silver?
So let's slow down.
Okay.
Let's think about the chlorine test overall, so we can think about what it's trying to get to. Now, obviously, we want to test for chlorine.
Yes.
What do we do in part A? Just what do we add?
3 molar HNO3.
Thank you.
See ya.
And 1 drop of 0.3 molar silver, what is that, nitrate?
Yeah. Okay. Now, what's going to happen?
There's a common
Is-
ion.
So, yeah, NO3 is going to be a common ion. Is the chlorine going to interact with the H or the NO3?
The H.
Would we form HCl?
No, because HCl is the strongest.
Correct.
Yeah.
So, let's see, will the Cl interact with the Ag or the NO3? It'll interact with the Ag. We're going to form an AgCl precipitate. Funny thing, why do we add the nitric acid? I'll give you a hint, carbon dioxide.
Oh, that's because so we didn't form the carbonate something precipitates. We're preventing some precipitation.
Yeah. The only reason you're adding the 3 molar nitric acid is to make sure that you don't have any carbonate ions in solution. Because if you had any carbonate ions in solution, you would actually precipitate silver carbonate rather than silver chloride. You'd get a false positive, essentially. So part A, all we're doing is we're creating the silver chloride precipitate. Now we want to do something to prove that it's chlorine that precipitated and nothing else, and that's where we go on to part B.
Yeah.
So what do we do in part B?
Part B.
What do we do?
I don't even know. So we add 3 more drops of silver nitrate and mix, centrifuge, then discard the centrifugate.
Right, so we're getting rid of the liquid. Essentially, we're keeping the precipitate.
And then we add a lot of water, centrifuge, discard again, and then add ammonia?
Yeah. So the whole centrifuge discard, that's to make sure we're cleaning out all of the iodine and bromine and fluorine. Iodide, bromide, fluoride. Right? We want to get rid of those other ions. We just want to keep the silver chloride precipitate. And all of those things do precipitate with silver, but I think they also precipitate with silver. We have to look at the KSPs to tell for sure. But silver chloride is going to precipitate the most. So those washes should get rid of the other ions, so we can go on to this next part. Then we keep the solid, add water, and then we add NH3.
Yes, that's where I got really, really lost.
And that's why I said, oh, yeah. Because we are a little bit behind in our class, and we haven't gotten to metal complexes yet. So what happens is the silver and the ammonia interact. So if I have NH3 plus AgCl, this goes to Ag NH3 2.
Where'd you get NH3?
We put it in there. There's like, we like put drops of NH3.
You form what is called a metal complex. So essentially, when we start to look at how does silver interact with chlorine versus how does silver interact with ammonia, it actually interacts with the ammonia better. That interaction makes it so I formed this weird metal complex, and this should look weird to you.
Yeah, it looks really strange.
It looks really strange. So what we're about to get into is, I didn't want to start talking about metal complexes till after the midterm, but I forgot about this part of the lab, so oops. I should have just talked faster through buffers. But what we have going on here is essentially the silver has d orbitals. The d orbitals on the silver allow things that have lone pairs to donate the lone pairs, right? So essentially, you can look at this as like a Lewis acid base reaction where the NH3 is acting like a base, silver is acting like a Lewis acid, right? Electron donor, electron acceptor. And the NH3 is going to displace the Cl, so the Ag is going to interact with the Cl. We can look at this in terms of the KSP for AgCl versus what we call the Kf.
So this is the formation reaction for the silver complex. Is what you wrote on the board.
Yeah, the silver, so the KSP, let's write down these two things. The KSP would be AgCl solid going to Ag plus Cl minus. That's the KSP. The Kf would be Ag plus 2 NH3 goes to Ag NH3 2 bracket to represent as a complex. That's the Kf. We haven't gotten to that yet. But what the idea here is, It's kind of like, do you remember the oxalate test from week 2 of lab? Just say yes, I'll feel better.
Yes.
Oh, great. Okay. So in that test, we essentially made like 4 precipitates, and then we only dissolved 1 by adding the correct acid.
Mhm.
Right? We added acetic acid. We added a weak acid instead of a strong acid, so it would dissolve all of them except for the calcium oxalate. That was in the calcium test. Yeah, calcium test. So this is kind of the same thing, right? I've got a solid that's forming, and I want to add the right material that's going to dissolve that solid, but not other things. So if I add this, essentially I should find that if I compare to AgCl, AgBr, and AgI, these other solids that form, only one of things. Only one of those 3 is going to dissolve when you add the NH3. So for each of them, we compare the KSP to the KF. Whichever one has the bigger, whichever one has a KF bigger than the KSP, that one dissolves. And what we should find is only one of them dissolves. It's the AgCl. So we then continue with this test, right? So that's part B.
Yeah, so then for part B, it's like I think that's what we do. We do like those reactions, and then it says repeat for silver bromide. And then for part C, mix thoroughly, then centrifuge and transfer, centrifugate into a clean tube. Add 2 drops of 3 molar HNO3. And then there's a white turbidity.
Yeah, so is that part C?
Mm-hmm.
So in part C, what happens is essentially everything should be solid except for the AgCl, right? The AgBr and AgI should still be solids. So we get rid of those solids and we just keep the solution, because now our chlorine should be aqueous, right?
Mm-hmm.
So we can keep that chlorine, and then we can get rid of the NH3 by adding acid, turn it into NH4. Silver will go back to the chlorine.
Okay, so when it says write the reaction that shows the acid protonating the ammonia in the complex and allowing the silver chloride precipitate to reform, what is that even asking?
If NH3 is a base, what's the acid-base reaction with a strong acid?
It turned into NH4.
Yeah.
That's it? That's it?
That's it.
Oh, okay.
So if this NH3 picks up a proton and becomes NH4, it no longer attaches to the NH3, or no longer attaches to the Ag. So if you do that twice, you just put Ag plus back in solution, then the Ag plus will interact with the chlorine again.
I'm gonna rewatch this one.
I'll also make sure I mention it at the end of class tomorrow.
Was like I love it.
You do,
Yeah.
but classes before that. But
And I have a class right after yours too, and then lab.
Oh my god.
that's exciting.
I'm
It's
trying to
great.
decide whether I should even go to one of my other labs tonight or not.
What time is it?
3.
Oh, it's 3. Hopefully that was helpful.
Yes.
I'll go ahead and upload this now. Goodbye, everybody.